Thank you, Bernard. Good afternoon. Here is my agenda for the next 30 minutes. I will focus here on the vision, the SAAB vision for the future regarding software technology. And I don't know what software technology is. It's no problem. I will take this opportunity to reflect over computing history at SAAB. Where we are today, the evolutionary trend, the explanation why we are where we are, our strategy, challenges for the future, disruptive challenges, and of course we try to give you a picture about the challenges that we put for CASTOR. That's the main. I will use avionics as an example in the presentation. But of course, SAAB is a big company. We have a lot of activities under the water, on the surface of the water, on land and in air. So we are wide, even if you see the avionics. Oak is my favorite tree, actually. It has power, it survives, and it has wisdom. And I grew up very close to the forest and water, and woodwork is my great interest. My name is Ingemar Söderquist, as you heard. I have a PhD in electronic components from Linköping University. My thesis was CMOS circuit for RF systems. I have a focus at that time on high-speed electronic, high-speed signal processing, scalable systems, and that time. I have been at SAAB for 40 years, almost 40 years. I'm now a technical fellow within avionic design, and I have a responsibility for flying computers, the overall technology, research, planning, widely. So, here, I will not go into the details here, but this is actually the words to take away from this talk that I want you to remember. So I will come back to this. It is determinism, security and safety, machine learning, complexity wall, and executable specifications. That is the main message. But if we start with the history, the Swedish history of computers started 1948. Maybe at Chalmers, I'm not sure. It was actually with a BESC. I suppose you ever heard about that computer. It's the binary electronic sequence calculator. It was actually the first in Sweden and probably also the first in Europe. In May 1954, we had the first programming course in Sweden. I don't know if that one was given by Chalmers or not, or actually who did it, but it was the first I have read. And SAAB actually was a big user of this machine, actually the biggest user. So SAAB decided to develop this machine further, and it became SARA, that was in operation 1957. And that one went to aircraft in the future. At the same time, I'm still in the history part here, at the same time, 1958, the integrated circuit was invented in the United States. It was actually Kilby from Texas Instruments and Noyce from Fairchild Semiconductor. And they both filed the patent at the same time. So it was actually a patent war at that time. And Kilby, he got the Nobel Prize. It was actually here in Stockholm. And Noyce, he won the patent. It was not that. But they are both regarded as co-inventor of the integrated circuit. It's interesting because parallel with that patent war between Texas and Fairchild, SAAB started in Swedish typarbete for the new aircraft AJ-37 Viggen at that time. And here is the system drawing of the aircraft. After a lot of discussions, they agreed to put a central calculator, a central computer in that system. And it was called centralkalkylator in Swedish. CK37. I have never seen that machine, but I will look for it. Actually, it was the first airborne computer in the world with integrated circuits. So SAAB was actually the biggest customer of Fairchild at that time, in parallel with NASA. And it's interesting to see that computer, each of them had actually about 3,000 of integrated circuits. And this development was made for only 6 years from the start of designing the computer, the software, testing the software, and actually fly with the aircraft. That is amazing. At that time, our famous Gordon Moore was working at Fairchild. He was working with production cost and optimization of production. He was actually working with the yield. And he noted on the figure in the middle that for simple, not complex circuits, actually the cost per component was inversely proportional to the number of components. So the curve went down when you added more devices in the integrated circuit. But he also noticed that when he add more components due to the yield, the cost goes up again. So what he found was that there is a minimum cost per component for each new technology node. A new technology node is what we remember as the 100 nanometer technology, the 90 nanometer technology, and so on. So what he did was to put them into one line, and he drew this line, and that is what we know as Moore's law. And later, also it's interesting to see that Noyce and Gordon founded Intel 1968. And it's probably not known, but Intel is the combination of integrated in integrated and EL in electronics. So it's integrated electronics is the name of Intel. Then, after 25 years in the United States, they created a first roadmap for semiconductors, the national roadmap. You will see later why I'm following this track. It was 92. Then a couple of years later, 2001, we have the first international technology roadmap for semiconductors, where not only the United States, but also Europe, Japan, Korea, and Taiwan was involved. So it was wide. most important is the core message from that roadmap, saying that the cost of design is of greatest threat to the roadmap. The cost of design is the threat, nothing else. And the roadmap itself was updated every second year. It was used for guidance for industry, but also it was important to be used as a clear target for research and really helped in the academia to focus on areas that needed research breakthrough. So it was a tool also at that time. Later, in 2012, the rebooting initiative was created that focused a lot on big data, machine learning, complex software issues and so on, to add those to the first initiative. And last year, 2016, the roadmap was changed from technology only to more a roadmap for devices and systems, where they merge very much more on the software side. And it also placed under the umbrella of IEEE and standards. So, but if we look on this roadmap, and this is the 2001 version of the roadmap, you can see here that 2001 is in the center of that picture, and you have 15 years of history and 15 years of forecast. And you have two curves. The blue one is the design cost without any innovations in the area. And the red curve is the predicted design cost for a system taking into account innovations. So this is actually a tool to predict and to control design cost for the industry. We can see here at that time, 2001, it was a history of four very important methodologies that was invented, really that was used to bring down the cost. It was some in-house tools. It was a special engineer that was very, very thin and could work in a lot of different areas. It was the large block and small block reuse, what we nowadays can see as software reuse and IP reuse. And also at that time, it was some improvement that was planned. It was for a more semiconductor implemented toolset, but also intelligent test benches and electronic system level methodology. The intelligent test benches is actually focused on software modeling. It's focused on formal methods and on automation of tests to increase the quality of software. So that was predicted. And if we look 5 years later then, and that is the updated roadmap for 2005, we can see now that this electrical system level methodology is in the center, but we can also see that there is a forecast of different methodologies that will be used to keep down the design cost, the blue curve there. And we can find now the system level design that goes beyond software and hardware system design tools. And we also have the executable specifications predicted in 2018. And if we then go another 5 years ahead for the roadmap for 2010, we can now see that the intelligent test benches are in the center of the drawing, but we also see a software cost peak there. And that one is actually telling that the research and the development could not really address the issue. The cost was higher than predicted. And we can also see that the executable specification and system design automation have been moved to the future, 2025. But anyhow, this is the tool for working with that. And SAAB then, in parallel with all this Moore's law and roadmaps, the number of computers in each aircraft have been increasing from 1 and then to 5 in JR37 Viggen, to 40 in JAS 39, the aircraft that is in operation right now. And in aeronautics, the traditional way of architecture was replaced by the integrated modular avionic scheme. I will explain what that is. But it replaced the federated architecture that was building on the principle one computer, one function. So it is more integrated. The enabler for that shift was actually the deterministic behavior. So that is the naming, deterministic behavior. And it was mostly achieved by the RINC 653 standard that created a time-space separation, and the RINC 664 that bounded the latency in communication. So it was the two most important things. Then in 2005, the first flight with Airbus 380 took off, and it was actually the first implementation of that software architecture. It was followed by Boeing 787, the drivvagnar. And all years here are actually referring to the first flight of the system. Now, if we go further, in Europe there was a lot of big programs that, and I just mentioned two here, Scarlett and Ashley, that started with the architecture from Airbus 380 and developed it further. It is called the IMA second generation, and it's there for the next generation of aircrafts. This architecture is actually a distributed modular avionics. The picture up there is what is actually flying on aircrafts today, and the second generation, I will explain that on the bottom. Most important is that the I/O resources have been separated from the computer model, actually, and are placed on the network. And that actually gives more possibility to adapt the system to different needs in different aircrafts, so that the I/O is not connected directly to each box here, as it was in Viggen and Gripen today. The second thing what happened was that it was then possible to increase the performance of the computing modules, and that actually enables for a lot of new functionality on each unit. And then there is a provided platform service level, and that actually gives some new properties, but also an isolation layer between the operating system and the applications. And finally, an integrated process and tool set on top of it, instead of having a separate tool set for each box. And that enables for model-based design. It enables for early validation and maturity. So this is the system thinking. Now, if we jump to today, I suppose you all heard in society the word digitalisering. We have always heard that. Digitalisering. And we have all, for decades, we have seen the CPU performance, the Moore's law there, but we have also this new figure that maybe you all have seen, but it actually tells that the single thread performance is decreasing and the frequency is decreasing. So the performance of our software system is going down. And you can always argue if this is wrong or correct or something, but something is happening. And actually, this evolutionary software scaling have ended. That's actually what have happened. Because the feature scaling, which is called a technology node, is nowadays limited by cost and the size of the atom. So it will not happen anything. The frequency scaling that involves the data transport is limited by the speed of light, so we are there. And our famous multi-core scaling is limited by the power and shared cache access, shared resources. It's limited. So what I'm saying is that Moore's law is dead. You should say yes. But it's actually the economic limit. It's from the economic point of view. This minimum in cost, the famous Moore's law, is dead. So the question is not how many transistors that can be squeezed into a chip, but how many chips that can be squeezed into a warehouse. So it's a data center cloud approach. Moore's law is irrelevant. It's totally irrelevant for this discussion. What we need now is this new non-formal computing architecture. And that gives us new challenges in parallelism, algorithms, languages, and system software. And this is actually what is addressed by this rebooting computing initiative for the road mapping. But we see a lot of other interesting things there. Microsoft has this intelligent cloud, and actually that is for real-time artificial intelligence and machine learning. And it has a new architecture. It has new, very, very powerful, deep, new network processors, the DNN processors, that they actually fit into the architecture in between the traditional CPU layer and the network to increase the capability of the system. Okay. So, and you also see that this cyber physical system that is a combination of the technical Internet of Things, and 5G vision. The focus here is on this 1 millisecond round trip latency that is very difficult to achieve if you go to the cloud and back. So the concept of edge computing is developed. And of course, one main challenge is that to make use of all data that is produced by the Internet of Things, because it will actually load the network. Long-term industrial need, if we go back to it, for system industry in Sweden, and of course avionics and other, it's actually that our future product will have increased functionality and level of automatization. So, and that will depend on reliable and increasing power in the computer, together with predictable development time and cost for software. So, we need architecture and principles for scaling. We need focus on security and reliability. We need cost-efficient design methodology. And the strategy to achieve that is to focus on computing power, security and reliability, and cost from three perspectives: from architecture, component, and methodology. And CASTOR will target research for future products, of course, but it's also obvious that the components, the software and hardware components of today will be obsolete tomorrow. So they are of no use. So the focus should be on architecture and methodology that will be used together with components of tomorrow with a 10 years perspective. And remember what is up there. The performance of a system is not controlled by the components, but by the way they are connected. That is very important, not to focus on too much details. So here is the big list now for some expectations. First, contribute to flat system development cost. That is why I showed the cost model and the international roadmap for device and system. And that should be done by developing software methodology, of course. Second is to develop software design and verification methodology that guarantee full function and performance at each product deployment. No update or bug fix allowed. It should work from the beginning. And that is very important for some type of systems. Of course, we expect CASTOR to follow international progress, assess findings, contribute to this methodology, and bring it back to Sweden. We focus on system design automation and executable specification with a specific focus, of course, on software system complexity, how to describe and evaluate. Of course, in the cooperation, CASTOR should understand the safety concern for determinism and use of shared resources, build up knowledge that is relevant for the industrial environmental needs, including safety and security, but also certification requirements. So that the system, that the technology that is invented really fits into the system, because it's very difficult and costly to add that later. And of course, cooperate with teams outside the center to understand the complete big picture for artificial intelligence. And the potential for this is enormous. And the question is software maturity for design and verification today where hardware was 1960. It might be so, because what we have today is artistic software architecture. We have these human boxes and arrow. We have manual code inspection. In some ways, software is where my presentation started, 1960. And you can see the old guy there designing the system, and they are putting it together manually. You can see that as a code inspection, and that is a UML drawing. This is the short version. Thank you.